Okay, I think we're about ready to get started. I see people still trickling in, and that's just going to happen. So good morning, everybody. My name is Kelly Hattori, and today we are having Kristie McLin of ConocoPhillips give a talk on her work in inorganic geochemistry and oil and gas industry. So and applications for it. So I'm really excited for this talk. Before we get started, I just want to remind you guys that next week, April 1st, which is April Fool's Day, but I'm not joking here. Next week, Ning Ling of the Bureau will be giving a talk on her recent work. So catch that if you can next week. And just as a reminder to everybody, if you would please hold your questions till the end, just so we can stay on time. And then if you want to write your questions in the chat box or save it so you can unmute later, you're welcome to do either. And until then, let me give Kristie's introduction and we can get this show on the road. So Dr. Kristie McLin is the manager of fluid characterization team at ConocoPhillips. In this role, she leads a team of scientists to support the global portfolio of ConocoPhillips and to develop leading edge technologies in the disciplines of geochemistry and basin modeling. Dr. McLin has served in numerous roles within ConocoPhillips, including Senior Advisor Supply Chain Sustainability, Water Management Project Lead for the Mid-Continent Business Unit, and Senior Geologist in the Reservoir Quality Prediction. Prior to joining ConocoPhillips, Dr. McLin conducted geochemistry research related to exploration and production of geothermal systems at the Energy and Geoscience Institute at the University of Utah and consulted on these topics for industry. So Kristie's got a lot of expertise here and I'm really excited for the presentation. So let's turn it over to Kristie.
All right, thank you. And just to let you all know, I know this presentation might be a little unconventional compared to some of the research topics you're used to seeing. And as such, I think it allows for a little bit more dialogue and conversation during the presentation. And I'm really hoping that we'll get to have some conversation and maybe you'll start to think a little bit about what types of research you and your groups would like to do in support of the industry and think about the things that are still out there to be discovered. So just feel free to type in the chat or raise your hand and I'll try to make sure we have a good dialogue about the types of things we're talking about today. So with that, I will share my screen. I hope it works the second time. Share, okay. Can everyone see that?
Oh, yes. Sorry, I realized I was muted. Yes, perfect. Everything looks good.
All right. Great. So we'll go ahead and get started with, yeah, so you heard in my bio a little bit about my various career, adventures. I actually started out with geomorphology as one of my main focus areas. And then I moved into geochemistry, and with geochemistry came carbon sequestration and geothermal. And this was back in the 90s. And then, interestingly enough, a lot of those things are coming back around again. So it'll be interesting to see where those things go. But interestingly enough, water geochemistry might be a little bit underappreciated in the oil industry, which is kind of strange because there was this book written called Geochemistry of Oilfield Waters in 1975. And so it's very interesting that there was a lot of focus on interpreting oilfield waters and understanding the science of oilfield waters and where they came from and understanding how that helps in petroleum geoscience and exploration. And I thought it was really interesting that when I came into the industry, it seemed like the science had fallen out of fashion, and that I had to reconvince people that water geochemistry would actually be a useful tool in reservoir characterization and in other applications. And that was a little strange for me coming out of geothermal, because in geothermal, all you have is the water chemistry to tell you about the subsurface. So a lot of tools that I brought into back into my work here at ConocoPhillips were taken from the geothermal industry. And And, just wanted to kind of talk about how water chemistry is geology and how we use it. And then as I get into my next slide, I have to give you my disclaimer. I'm here today as a representative of, geochemistry and of myself. And so all of these words are my own. None of them belong to ConocoPhillips. And so ConocoPhillips said, yes, you can give this presentation, but make sure you give the disclaimer that these are all your own words. So if I say anything stupid, blame me entirely and don't go back to ConocoPhillips to say, hey, you said this. But that being said, I hope to represent, what we're really concerned about in the industry when it comes to using water geochemistry and what kinds of research we're trying to do and what we would be really interested in seeing more of in the future and why. And part of the why is this next slide. So as geologists and as geochemists, we have a language that we speak. And our language of water rock interactions is very different than the language used by drillers and completion engineers and reservoir engineers and production engineers, but all of them are speaking the language of water rock interactions as well. So it's when you go out and when you're looking at research being done in the fields of drilling and completions, reservoir engineering, production, you'll see a lot of these words. And a lot of these words mean the same things as words we use as geologists and geochemists, but it's hard to understand that we're all speaking the same language. So, and I'll just start with drilling and completion. So fluid compatibility, we're worried about whether or not drilling fluids, which are mostly water and minerals, and then also completion fluids, which are mostly water, are going to be compatible with the reservoirs. And you can have all kinds of things happen as a result of the interactions of these fluids with the rock. And some of them could be, for example, rock softening or weakening. So you want your rock to remain competent as you're drilling through it and as you're completing your wells. And so making sure that the fluids, the water you're using is not going to create challenges by, creating all kinds of negative reactions with the rock. Or even enhancing positive reactions with the rock. That's all about understanding the chemistry of your fluids, both subsurface and the ones that you're using in your operations. Proppant embedment is talked about somewhat in the research about how, the proppant grains are all quartz for the most part, and those quartz grains are pretty hard, and some of the rocks we're placing them into are not very hard. And then also those rocks are not necessarily glued together or cemented together. They're just held together by the weight of the earth. So when you open the earth up through the hydraulic fracturing process and you're putting proppant into the rock, it's not just the weight of the rock, but research has shown that the water interactions with the rock can even further cause proppant embedment. So understanding when that's going to happen, where it's going to happen, and the circumstances under which that happens is pretty important, because we're putting a lot of time, effort, and money into opening this rock and keeping it open, and that's our pathway to production. So if we're doing something that then closes those pathways off, we want to prevent that as much as possible. The word leak off is used, and I think that word is kind of interesting, because I've heard completion engineers say that water doesn't interact with the rock except for in the process of leak off, which is kind of funny, because leak off is the process of your water going into the reservoir. And that to me seems like a pretty significant interaction of the water in the reservoir. So I thought it was interesting that they kind of diminished the impact of water rock interaction by just saying, oh, it's just leak off. And then, clay stabilization is a term you'd probably hear a lot from completion engineers. And that's, trying to keep clays from swelling or clays from migrating where they're not supposed to be. And so in order to do that, they use just simple chemistries like potassium chloride or things like that to try to keep those clays from taking in the waters into their inner layers. And scale is another thing. So the word scale is basically when you're precipitating minerals in places you don't want to precipitate them. So within your fractures, within your fracture mouths, just that entrance of the fracture into the wellbore, in your wellbore, and then up in your equipment. And that happens when you change pressure temperature of your reservoir fluids, or when you introduce incompatible fluids. And so making sure that that is not another mechanism for damaging production is very important focus area. Wettability alterations. So there's a lot of talk about surfactants and whether or not they help aid in production. And in the case of conventional fields, they've been used pretty regularly. So they just grabbed them and applied them to the unconventional fields. But there's a lot of questions as to whether or not those things actually work in the same way as they do in conventional fields. A lot of times the molecules are bigger than our pore throats. So does that really enhance productivity or inhibit? How does that work? The word osmosis, if you're using fluids that are more saline than the fluids in your formation, you're drawing fluids out of the formation into your wellbore as you're drilling, right? And vice versa. So osmosis is a well-known concept for drillers, and that's how they decide to weight their muds versus what they're drilling through. And this is particularly important as they're drilling through mud rocks, essentially, because they can have some different salinities in that area than they do just drilling through conventional sand reservoirs. And then you get into things like very, very similar concepts in reservoir engineering, but they use different words. So skin is what they use for formation damage, and that formation damage are some of those words you saw in drilling and completions: rock softening, weakening, scale, clay, stabilization, things like that. Water block, that's basically where you just form, with the capillaries, you basically trap water within the pore space just because of the surface tension of water, for example. And that varies depending on chemistry. So that's of interest to reservoir engineering. Finding ways to enhance recovery through modification of the fluids you're using is very important to reservoir engineering. And then conformance, keeping the fluids where they belong in the formations they belong in, and in the wellbore is quite significant. And then the words for geoscience probably. I just wanted to point out that when geoscientists say the word cement, it's obviously not the same cement that other disciplines are talking about. So you have to be very careful when you're talking to these other disciplines about a cement that is holding your quartz grains together. You might want to choose a different word or use a qualifier, mineral cement, or something like that. Just a word of caution out there for those of you who hang out with engineers quite a bit. And then on the production side, same thing with scale, fines migration, clay swelling, but acid compatibility is one, right? Because we use various acids for cleaning out our wells. So we have to think about what kind of damage those acids might do to the formation. Obviously, you don't want to hit some clays with HCl, for example. And so understanding that and understanding the good and bad that could happen is critical for production engineers as well. And actually, when I first started in the oil industry, one of the first production engineers I met was a geologist. And so I thought that was really fascinating. And I thought it was really cool to see that, geoscientists can work in all these other areas because they understand process, they understand mechanism, they understand how these things happen and what's important. So are there any questions or comments at this point about all these all these words and how they relate to geoscience and how they relate to the reservoir and how they relate to the rocks. All right. I don't know how much of this you all already knew, but I just found the language barriers between geologists and engineers to be quite fascinating when I first started in the industry. And so you all are familiar and know and love the periodic table of elements, I'm sure. And this is really, you know, what it comes down to with geochemistry and what we do in the oil industry is back to this, right? And back to just basic chemistry, you know, plus geologic context. So we are using cations and anions that are in the water to tell us about what's happening in the subsurface. And so just to refresh for those of you that it's been a while for that you took a hardcore chemistry class on, when we're talking about cations, we're talking about an atom that lost electrons. And then when we're talking about anions, we're talking about the atoms that are gaining those electrons. And they do that to form more stable configurations. And so the cations and anions in the fluid are, of course, our first stop for what we're analyzing in the fluid to understand what's going on in the subsurface, because those are all either from the original water or from a fluid rock interaction or both. And trying to deconvolve that and understand that is, of course, a lot of what we spend our time on. And then just to refer once again, if I start using language, I know language can be a huge barrier in science and engineering, so I want to cover it first. You know, just there's the normal ionic bonding, which is an anion and a cation, where they are transferring electrons. The covalent bonding, where atoms are sharing electrons. Metallic bonding, where electrons are just floating around in space, basically around all of the atoms. And then the reason I want to talk about molecular bonding a little bit and that weak electrical attraction is because that's a lot of what we see in mud rocks, for example. So again, those rocks are not necessarily being held together by the strongest type of bonding action possible. Little pieces of clay and little you know, other minerals are not necessarily fully cemented and competent in all cases. They are in some, but they aren't in others. And so because electrical attraction is all that's holding these rocks together, in some cases, you're going to see a lot of potential negative interactions when you go in and disrupt that. And so that's critically important when you're thinking of drilling and completions in these rocks. And we've seen some cases where you know, there have been negative results reported industry-wide on certain completion fluids that cause more of that disruption of that electrical attraction and just basically can turn the rock into goo. And we don't want to do that. So I think it's really important just to go back to the basic fundamentals of chemistry to figure out why that's happening. Because I think in a lot of cases we don't. We just start with assumptions. We don't necessarily think about how all these different things come into play as we're introducing fluids into the rock. And so, you know, again, sort of thinking in that process, in that basic mode, you know, when water contacts rock and we have a undersaturation of certain minerals with respect to the pressures and temperatures, the rock's going to dissolve. If we have a supersaturation, we're going to precipitate. That's, you know, that's just how it works. However, sometimes these reactions are fast and sometimes they're very slow. And so knowing which reactions are going to happen when is really important to a lot of processes we see happening in wellbores and in reservoirs. And so, and these rates are impacted by those changes. You know, it's the chemical potential, it's the temperature, it's the salinity, it's the pH, it's the microbes. And I'll talk about this a little later, one of the most understudied things I think in geochemistry is the impact of microbes in the subsurface on these interactions. I've seen some weird stuff that I can't tell you about today, but I am just saying microbes are super important. So that geomicrobiology, I think, is a frontier that if anyone here is interested in getting involved in, I think that's going to be pretty big. And not only big for the oil industry, but big for every other industry out there. I just think it's underappreciated how much the activity of microbes contributes to geologic processes in a lot of cases. And so, you know, it's really interesting. Those of you that are geochemists, if you're willing to admit, we know a lot about geochemistry, but for example, precipitation kinetics are yet another field in which we keep seeing things that blow our mind almost every day, like things that shouldn't be happening if you use like conventional wisdom or what already has been published out there. So precipitation kinetics, and again, what impacts that in the chemistry, in the subsurface. There's so much left to study and so much left to learn in that field that you know, it gives me a lot of excitement when I wake up every day thinking of all the science we could be doing. So, and then, you know, stable isotopes, we use stable isotopes quite a bit in water, but also in a lot of other applications in the oil industry. So, you know, there are commercial labs that offer isotopic analysis for us for that reason, and we keep them pretty busy. So, you know, the easiest ones, of course, are hydrogen and oxygen. I mean, they tell you so much about where that water's been, what it's been up to. Is it, you know, is it a meteoric water, or is it a connate water, or what kind of water is it? Because you know, the Permian Basin, for example, is just such a mix of all kinds of waters getting into all kinds of places from all over, right? You've got meteoric water coming in from the Guadalupes down into pretty deep in the basin. And so being able to look at the stable isotope profile of that water gives us a lot of information about how recently did that water get there, and you know, how does that impact what we're thinking about from a petroleum system basis of the evolution of this basin, and where oil should be and where it migrated to and all those things. So again, just I think underutilized tool in a lot of cases, but critically important. And then, you know, I already talked about clay mineral chemistry a little bit, so I'm not going to go into detail here for the sake of time. But, you know, the behavior of clays changes when it's introduced to different pHs and different chemistries of water, partially back to that whole, that the chemical bonds, you know, that I was talking about earlier. And it's very important to understand that. So some minerals are much more stable in certain fluids, certain pHs, certain salinities, certain compositions than others. And so as complicated as it might sound to have to think about all those things, it's very important that we do, to make sure that we're giving our wells the best chance of life for the longer term. And so, yeah, and I already talked about clay swelling, so we'll skip ahead. So the reason I kept this section very simplistic rather than sort of, hey, here's some high level researchy bits of information. First of all, the lawyers, as I mentioned earlier, making sure I could give this talk, but more so we can talk about the why of how these methods and why they're used and the types of applications they're used in. So this is maybe where some more dialogue might come in, I hope, and we'll have some more questions and discussions. But I just, of course, disclaimer after disclaimer, you know, I've run into a lot of people who just grab these techniques and they use them without really understanding why they would or what they are. And so it's always best if you can work with a geochemist, but then also understand the limitations of these techniques. I mean, so important to think about the failure leg of where things could go wrong in your interpretation, and to stay humble, essentially, because again, if we knew everything, like if I knew everything, I'd be off rich on a private island somewhere because I would be selling the most awesome product on the face of the planet that makes the best things happen. But there's so much left to learn, and we just need to start from that place of humility that the earth is going to knock into us every chance it gets, right? Which is, that's why we're scientists. That's why we love science. So just be, word of caution. So most of you will have probably taken some kind of basic hydrology class or basic geochemistry class where you would maybe have seen some of these traditional water geochemistry plots. We've got stiff plots, we've got radial plots, we've got just like, so many different kinds of plots that we can use, and a lot of them are common and a lot of them are less common. But the main point about these plots is that they're really good for environmental applications, but they don't necessarily give you the nuances you would need for reservoir geochemistry. And so they're very simple, they're very straightforward. Almost anyone in almost any discipline could apply these. Reservoir engineers apply them. Just people in like tech positions who are just putting together data for scientists to evaluate can do these things. So they're accessible, they're easy, they're consistent, but again, they don't give you the level of detail you might need for some of the more high-end applications of geochemistry. Now, not necessarily a higher level of technical in making the plot, but maybe trying to understand which ratios you would use or which elements you would use to make these plots. Now that's where sort of the level of expertise needs to come into play. So of course we love cross plots, we love cross plots of ratios, we love machine learning, we love all of these things that give us beautiful trend lines and beautiful clustering of data. But the real thing that I always want to emphasize is that it's not about it's not necessarily only about the relationship of the data you see, but it's about explaining why that relationship exists and why those things matter. So this is an example from a paper that we did in 2019 for the Eagleford, where we were looking at the fingerprinting of different waters from different zones and different areas, different locations we were looking at. And this was just one example out of many in that paper of things we use to type the waters and then look at the variability within those types of waters. So that's what, when you're looking at cross plots and you're using them for reservoir geochemistry and you're trying to do things like production allocation or understanding which zones you're contacting and draining, understanding not only, the clustering of the data, but the range of the data within a formation tells you a lot. And it also can come back to when you're mapping out your field, when you're mapping out the area, when you're mapping out sort of where your sweet spot is in a basin. This could give you a lot of information because you'll find that as you're sort of pulling apart this data and as you're starting to understand why is that potassium strontium ratio variable across this area, and is that variability real? Is it within the range of interest, or is it within, okay, maybe that's just the range of our sampling or whatever it was, or our analytical error. But as you're starting to pull that apart, you say, oh, this looks like it's in an area that had this type of mineralogy, which then represents this depositional environment, which then represents this assumed productivity of the organic matter. And really that's, I think a lot of people stop at the plots and don't think about process, don't think how it ties to geology, don't think about why that impacts where you would drill and why. And so, I think that it's important that as scientists and researchers that we never stop asking why, and we never stop trying to pull it apart and stop trying to see where it fails, where our assumptions fail. So again, simple plots, but deeper meaning here that we need to talk about. Time series, we do a lot of time series. And the reason we do a lot of time series is that our chemistry changes during production. That's oil, gas, and water. And you will see, I'm referencing our publication from 2019 here, but you'll see that in all of the time lapse or time series geochemistry presentations and talks you've seen throughout the industry. And so the reasons for why that chemistry varies over time, I think there's still a lot of information and a lot of research there to be done, because the process of why it varies and how it varies and what that means is probably quite important. In this case, our hypothesis and our interpretation was that we were seeing formation water become more dominant over time as the dominant source of the water we were producing. So that reservoir, that connate water that's in the reservoir, at the start we were recovering our fracturing fluid or our frac load, but then over time we were starting to see that contribution get less and less as we were getting more and more of a contribution from that formation water. And so knowing this behavior is one thing, but what does that mean? What does that mean as far as mechanism of what's happening downhole? I'll be honest on that. I don't think we as an industry still fully understand all of those processes of how, the fluids are behaving downhole and what that means to, does that mean something that we can use to determine fracture surface area more effectively, or drainage heights, or efficiency, recovery factors, things like that. Like, there's something here. And I wish I had more time to dive into it. And if you have interest and have more time to dive into it, I'd be really interested in hearing what you have to say. But there are still, we think we know a lot, but let's be honest, we still don't. We're still trying new things. We're still learning new things in these, mud rock type plays that I feel like the water geochemistry could unlock a lot of that thinking if we just thought about how that chemistry would be impacted by processes over time. Back to what I was talking about with stable isotopes. So same thing where we're looking at our contributions of production, where we're recovering that fracturing fluid versus recovering formation water. Stable isotopes are really helpful with that too, because if we're using some kind of surface water, or if we're trying to make sure we're not disrupting some kind of groundwater, it's good to know that those waters usually fall along the global or the local meteoric water line. And then most of the water rock interaction, and then thus connate water formation waters, head out off to the right to the heavier side of the oxygen side of the plot here. And so again, we can determine mixing of some of the waters we're using for fracturing versus some of the waters that we're producing from the zone of interest. We can understand what that recovery factor is. We can understand water saturations of the zones we're in. And then we can understand, what contributions from what zones are we looking at. So again, I feel that what we've done so far has been incredibly useful and insightful, but what more could we be doing with this data? Could we be taking it and learning more about the behaviors of the subsurface, the natural unaltered subsurface, and then what we do to it? Yeah, I think we could, but we have a lot of data, but not a lot of time. You all probably have more time and less data. So, is there something, if you went back and thought about it, is there something to this that you think could be done to try to give us more insight on how these systems behave? And then, sort of the more advanced techniques. It was very interesting to me, again, coming out of geothermal. All we had was water chemistry, and so geothermometers were king. I mean, we used whatever was in the water in whatever quantities to tell us what the reservoir temperature was. And if you're out in geothermal exploration and you're pulling surface fluids and you're seeing high silica content, for example, you're going to say, okay, there's a contribution here from some deeper, hotter source. And then you're going to go try to figure out where that deeper, hotter source is coming from, right? Interestingly enough, there are plenty of publications out there that utilize geothermometry for the oil industry. However, it's still an extremely underutilized tool in industry. However, there are so many uses of geothermometers. Again, just trying to understand, sometimes we get contributions of water from zones that we didn't think had water in them. And so by being able to use these geothermometers, we can say, yeah, we think it's coming from right around that depth based on our geothermal gradient in this area. And then we can start to understand, oh, well, maybe our petrophysical model was wrong, or, maybe we didn't understand something about the salinity, or, and then really work through that. And so the two types of geothermometers that I highly recommend based on experience and based on literature are this magnesium lithium one. It's from a publication on basin evaluation. And if you're interested, I can send you that paper, that reference. And then the silica geothermometers, which are great because those are not empirically derived. Those are based on thermodynamic principles. So how much silica could you dissolve into the water given certain temperature, pressure situations? So useful. And then once again, that's another place where I think more research on more types of geothermometers for the oil industry could be immensely valuable. And I know some research has been done in the past, but again, kind of fell out of fashion in utility. You probably all know and love the batch geochemical modeling where you put, gas, water, rock together and you see what happens. It's really fascinating to me that I see a lot of reaction path diagrams and things out of Geochemist Workbench. And while useful, I find in industry they're not nearly as useful as thinking through what would you say, process, right? What is it that I'm trying to model? I see a lot of students and a lot of research organizations just kind of click a few buttons and put some stuff out that's geochemically sound, but that doesn't necessarily mean it's representing the types of reactions or the types of things we're seeing. So I highly recommend that if you're going to be doing geochemical modeling for industry, that those students and those researchers spend a lot of time with not only geoscientists in the industry, but the completions engineers and the production engineers in the industry, because a lot of results we get back and a lot of results we've seen on projects we've worked on are not representative of what we see when we go in and we do the work in the well. And so I just wanted to kind of point that out and say that, and it happens to me all the time, even in industry, where I give results and then someone comes back and says, that's not what happened in the well. And now I got to go back to the drawing board to figure it out. But just from experience, the best thing you can do as a modeler, as a geochemist, is to talk to the engineers and really start to understand what's happening, not just in the natural system, but in what we did to the system and the circumstances of operation and the circumstances of additives and the circumstances of how things were done. So I just want to end, because I know we're at time, with a couple of things. Reactive transport modeling, I think it's been highly underutilized in industry, highly, highly, highly underutilized. And some companies are really good at this, but they use it for diagenesis and exploration. However, I believe there are a lot of processes going on in unconventional wells with hydraulic fracturing that could be simulated in a reactive transport modeling scenario. So rather than the batch models and rather than the reaction path models, I personally want to see more reactive transport modeling, and I can't emphasize that enough. And again, with the caveat of process. Like, are we really simulating the right processes? Are we really simulating what happens in the reservoir? What's going on, and microbes. So I'm going to end on that. We could do principal component analysis and chemometrics all day. I think biogeochemistry, as I said earlier, is the next frontier, and what I really hope that we as scientists start to progress towards. I have seen things come out of wellbore cleanouts that look extremely biological and mineral together in interesting configurations, and those things I can't talk about, and I can't talk about where, but I will tell you that these things are happening, and these things are important, and these things are impacting production. So we need to start studying this more rigorously. And this is a paper recently about the Bakken, showing abundance of different kinds of microbial populations, and then relating it back to the inorganic geochemistry side of things. And that is, it really needs to be done, because those microbes are causing things to happen downhole that we didn't even comprehend. And now we're sitting here with a puzzle, you know, with maybe not as many tools at our disposal as we would like to have to figure out what's happening and why. So I just hope that you know, someone somewhere will start to become a lot more interested, and that we can start to gather the data and collect the data and tie it to production outcomes a little bit more heavily. So it's not just biology, not just geochemistry, not just production. You know, these things all are happening together downhole.
Hey, Kristie, I've got just a quick question on this slide. What's the x-axis on the graph on the left?
So
The graph on the left.
Yes.
That's showing all the abundances. Yeah.
Relative abundance and different. I believe those are different wells, but
Okay.
I'll have to look that up.
Okay, so different Bakken wells that are showing different abundances of different bacteria and
correct.
Okay. Cool, great.
Correct.
Awesome, thanks. I was curious. And
yeah,
are those also
I guess I cut that off. Sorry about that.
That's okay. Are those also labeled on the PCA plot to the right there? Is that what we're looking at with the dot?
Yeah.
Okay.
Mm-hmm.
Cool, great.
Yes.
Awesome. Thanks. Sorry to interrupt.
No, I'm glad you did. So yeah, that's it. I'm hoping there are some questions, comments. I'm hoping that was actually interesting, even though it was a little bit different maybe than what you usually get. Yeah, so I have references in the back. You can have these slides. You can feel free to use them. You can feel free to distribute them. Again, they're all mine, except for the graphs in there, which I referenced to the appropriate authors. But I use this as teaching material sometimes. So feel free to use it as such if you'd like to as well.
Great. Well, thanks for a really interesting talk, Kristie. It's a really interesting, different take on geochemistry than the ones that we usually are used to approaching. So that's really interesting to learn about these different applications that you guys are seeing in oil and gas industry that are not necessarily being, you know, the needs aren't necessarily being met. Mm-hmm. So we'd like to open up for questions, everybody. Does anybody have any questions? You can unmute or you know, just write it in the chat box and I'll read it out if you don't have a mic.
Let's look like Natasha Morris had a question.
Yeah, I really liked, sorry, kind of
allergies, I know.
stuck in my throat. Yeah, I'm really interested in that lithium magnesium thermometer. I hadn't seen that before, so That's yeah, if you don't mind sending me the reference, I put my email address there. Yeah, this is a great talk. I'm a bit of a geochem nerd. More of my background is igneous, the igneous side, or that's where I started. But then I worked at Shell for 7 years, and then now I'm working with lithium brines in Alberta. So this is just kind of a culmination of everything that I've been thinking of. But just going back to your reactive transport, and maybe this is bad, I've never really heard much about this modeling. So I know the slide that you had, right? Maybe even if you could send some references or ideas kind of connected to this, because especially yeah, with the lithium brines I'm working on, I think this is a big piece that I haven't thought or didn't really know of yet, or had the right terminology sometimes to even look up these sort of things. So yeah, if you don't mind sending me that material.
I don't. Yeah, no, I don't mind at all. And, you know, sort of reactive transport modeling, I know I didn't dive very deeply into it, but my introduction to RTM came from carbon sequestration and geothermal applications. And so we used reactive transport modeling quite heavily in both of those applications. But I came to industry and I found that some companies used it. And again, they were more on the diagenesis side of thing. Oh, I'm going to model dolomitization and I'm going to see how these heavy brines sunk in and change the mineralogy. And then, but you know, as we're getting into these unconventionals and introducing, you know, large quantities of fluids into the subsurface, this kind of got largely ignored. And so, and so interestingly enough, you know, we're currently working with a reactive transport modeler now who used to work at another company, because, you know, that other company was more heavy into that. But, you know, we're finding some really fascinating applications as far as understanding, even understanding how certain metallurgies are interacting with some of our produced fluids and produced gases, and how that impacts things, you know, just, you know, there's all kinds of applications that you can do in this space with reactive transport modeling that, again, if you have the right sort of mental model built, you know, the right processes in place, the right understanding of what you're trying to get at, that you could really find a lot of value in this type of technology.
Yeah, thank you so much. That was an excellent talk.
Thank you. Yeah, and I'll definitely send those references, and I'll be happy to share some resources. Yeah, so Carl Stiefel and you know, there's a whole team of people up at Lawrence Berkeley National Laboratories who focus on reactive transport modeling, and the tough series of codes, tough React, all of those. I think they're actually giving a training next week too, so I could put you in contact with them if you're interested in taking that training as well. Excellent, excellent software, not very user friendly, so taking the training is crucial.
Yeah, if you don't mind just sending me the details, that would be great. Yeah.
Hi, Kristie.
I'm sorry, go ahead.
Oh, okay. Yeah, Chris. Yeah, yeah. I found this talk very interesting. Although I'm not a geochemist, I'm working more on the fluid flow aspect and petrophysics. So a lot of water rock interaction that will catch my eye, and I totally agree with you on many things. Like the leak off is a big evidence of the interaction. Yeah, people just simplify that as the, you know, using some simple model or in concept, but it's a very complicated process and very heterogeneous along the well.
Agreed.
So yeah, it's a lot of things, but one thing I'm not very sure is about this, actually you just mentioned about, is the reactive transport. Because yes, you mentioned that in carbon sequestration and others, but in unconventional, in mud rock, I think the reaction should be there, but the limiting factor or time limited factor is the flow rate.
Yeah.
Is how deep, how fast
Yeah.
the fluid can move into the metric. But in the fracture is another thing.
Yes.
A lot of
Exactly.
fractures, a big area of fracture, we have a big volume of fluid injected there, so we can expect something, as you mentioned. But in a matrix, maybe that's another thing that I'm not very sure, because the inhibition or the input of the water is so slow and so limited. But I'm open to that. I would love to talk to listen more about, the upcoming result from you. So by the way,
and I can comment on that just a little bit. Well, the first key, of course, is the history match, right? So if you've got a good data set of water production, you've got a good data set of XRD, XRF, mineralogy, thin section descriptions, characterization of the pore space. Those are all important for your model. But then there's the matrix part, there's the fracture part where you're almost modeling a sandstone surrounded by, mud rocks in some cases. And then there's the wellbore aspects. And so making sure that each thing is considered appropriately and each model that you've got the right approach to understand what your sensitivity analysis is really important to kind of hone in on what really matters and when it matters and where it matters, right? And so, those are all the kinds of things that make reactive transport modeling really iterative, especially in the oil industry, where just as you said, we're making a whole lot of assumptions. And so testing those assumptions in your sensitivity analysis is crucial. I fully understand what you're saying and the complications that arise.
Just another thought is not only it's playing a role in the production, but also in a geological time frame of oil and gas generation process, because that's oil push water out. And that affect many things, weathability and saturation, all those things. So that's another thing. I see many other questions, but I will just ask one short question here. So I see the colonite. You show the surface charge is changing with pH, but how about elite and smectite?
Yes. And I can give you the references I used for. Here's this Montmorillonite, which is
maybe one more next.
And there's the kaolinite changes with surface charge. I think there's a pretty sufficient body of research on individual clay minerals and their behaviors in different pHs and in different fluid compositions, that I think the information is there, but the fact that we haven't transferred that over sufficiently into a predictive capability, there's still a gap there.
Okay. Yeah, I still
can
have
I ask a question?
Sorry, to ask, but
I'm sorry.
I will stop here. Maybe I'll follow up with your email, right?
Yeah, feel free to follow up. I'd be happy to.
That'd be good.
Yes,
I think Mosen had a question too, and we're running out of time. So
yeah, we're running out of time, so I want to make sure I jump in before. So I was wondering, two questions real quickly, Kristie. First of all, thank you for your very nice introduction and presentation. It was very informative. I was wondering, what is your go-to reference for finding these reactions for minerals? For example, I know like kaolinite you've shown here, but I mean, like we've been looking for like information on K feldspar, for example, for various different pHs. So, and there's like various different papers, but we don't necessarily know exactly what the parameters should be for doing the reactive transports, and which ones to trust. So where do you go most often to find, a central location for finding those reaction parameters?
You have hit upon the classic geochemist thing that makes people yell at each other during conferences. We all have our favorites, right? So for me personally, when I do modeling, I like the Lawrence Livermore database. And I like to use the kinetic rates mostly from that USGS compilation. I think it's from 2003, I want to say, and I can send you that reference. However, I do try to keep up with current research in that space, and I do pull directly from papers. So start with the compendium. The reason I like the Lawrence Livermore database myself is because it contains more of the minerals I'm likely to encounter in a lot of the reactive transport modeling that I need to be doing. Now, that being said, I know lots of people like other databases and lots of other databases, and some people even build their own. You'll find that, for example, that within the Tough series of codes and Tough React, that they have kind of based their own database off of, like a Lawrence Livermore type of database, but then have made modifications that they've seen, necessary. The other thing that people do to kind of tweak the answer a little bit in reactive transport modeling, of course, is the accessible surface area of a mineral to that reaction. And so that is also the subject of much debate on how you would go about assessing that available surface area of the different mineralogy within your code. So I have my preferences as a geochemist, and I can tell you what those are, but I can also say that not everyone would, and people might even violently disagree with that. So it's just a matter of making sure the minerals reactions that you need available are in that database and in that compendium that you're using, that it is backed by maybe multiple modes of experiment, not just one experiment, but maybe multiple modes of experimentation that have gotten to that. Again, I will caution that I think a lot more research needs to be done in precipitation kinetics. I don't think we're there yet. I think, a lot of time we just take dissolution kinetics and put them into precipitation because that's all we have. But I know precipitation kinetics are a challenge, getting those precipitations to occur, understanding how fast they occur. Even 10 years ago when I was working geothermal scale, we actually went to downhole samples and found amorphous silica scale where quartz was predicted because it was more favored. But, as we went through it, we started to realize it made sense that amorphous silica would be what we found, that often what precipitates is actually the thing that's not thermodynamically favored first, and then it changes over time into the more stable form, right? So I think as we get more and more information and see more and more real data coming up from wells, when we do these wellbore cleanouts and try to get at these challenges, that we're starting to learn more that shows us how little we really know. So
thank you very much. I'll check with Kelly and get your information so we can exchange that references that you mentioned. Thank you so much.
I'll be happy to send them.
Yeah, we're starting to run out of time. I know that, so Lucy had her hand raised, and then Nate Miller had a question as well. We're out of time, but if we can make it, if we can make it quick, then Lucy, go ahead, and we'll see if we can stuff it all in. But if it's not gonna be quick, then I would encourage you guys to email Kristie.
Yeah, I might be able to just talk to Kristie privately. So how about you go to?
Feel free to give me a call. I'd be happy to take it.
Okay. Yeah. Thanks, Lucy. So Nate, he had asked a question in the chat, so I'm gonna assume that he doesn't have a mic. So he says, what geochemical analyses are routine and how many are one and done assessments, such as completed well versus ongoing monitoring related? Who decides what, for example, cations, anions, stable isotopes should be analyzed, and where's the work performed? He's saying that we have these analytical capabilities in Jackson School, but many of the labs could benefit from more collaborative work along these lines.
Yeah, absolutely. So who decides? Oh gosh, that's it's kind of a loaded question, I guess. It depends on the purpose, and I hate to admit it, but I think anyone in the industry would admit it. Oftentimes, left hand doesn't know what the right hand's doing. So production engineers will be off collecting samples and analyzing them for what's relevant and important to them. Completion engineers, same thing. Geologists and geochemists, yeah, we have our own uses, but a lot of what we're collecting could, benefit from a little bit more standardization of what we're collecting, when we're collecting, why we're collecting, and making sure it gets into a database of information that then, I mean, if we had that, we could then go off into machine learning space and get production data tied into completions data, tied into geochemistry data. And wouldn't that be a fascinating world to live in, right? So from my perspective, the things that matter most usually on the production engineering side are often related to scaling and corrosion. So they're going to be looking for maybe a lot more exotic metals than I would need to look for just from a, allocation or reactive transport modeling side of things. So you'll be thinking things like chromium and zinc, for example. I mean, less important that I get to that nuanced detail in some of the work I'm doing, but very important to understand on the production side, to understand where corrosion is occurring or where it could be occurring or where H2S scavenging is important on the geology side. So say I'm doing a totally different type of project and I want to understand the scavenging capacity of my reservoir for H2S. Then yeah, so some of that more detailed metals analysis is going to be a lot more important than just sort of your basic fundamental cations, anions. Organic acids, that's another thing I didn't really cover, but application of organic acids is critical in water flooding and in a lot of production assurance processes as well. So, maybe if you're trying to understand water washing or anything going on where, you're putting water into the reservoir and you're pushing oil out and you're trying to understand sweep efficiency, there are a lot of things encoded into the chemistry in the organic acid in the water that could give you information about how efficiently you're getting that oil recovery for the water you're putting into the reservoir. Stable isotopes, I mean, they're so cheap to do just hydrogen, oxygen. I think everyone should always do them. But then you get into a little bit more exotic isotopes and it's on a needs basis. Like, what is your question you're trying to answer? And is that question answered sufficiently with the basic analysis, or do you need to go that next step? When you're starting a new problem, you don't know, so you do everything, but then you're able to back off of some of those things later once you realize, oh, my chloride content and my hydrogen oxygen isotopes are telling me exactly what I need to know. You want the rest of the analyses from a QA/QC perspective, but maybe I don't need strontium isotopes. Or maybe I do. Maybe what I'm really trying to do is understanding, like, did this water come from this time period? So I'm really trying to tie the water production to, the stratigraphy. So maybe I want to go more detail into the isotopes, if that makes sense. So it's not a hard and fast answer. It's about what questions are you trying to answer? What are the discipline? What matters to those disciplines? And what are they looking for? But I do think it's good to talk to the other disciplines and start to collaborate with the other disciplines to try to consolidate and optimize that sampling and analytical program so everyone gets what they want in one sample rather than 50 samples being taken for 50 different purposes.
Cool. Okay, so I think that with that we're a little bit over time. So if any of y'all have any extra questions, you're welcome to email me and I'll pass you on to Kristie and we'll get you guys in contact. Otherwise, thank you so much, Kristie, for getting in for a talk. That was really fascinating. I really enjoyed it a lot. And as a reminder to everybody else, next week, April 1st, we'll have McLin from the Bureau giving a talk on her recent work. So with that, I'd like to say bye to everybody and thanks again, Kristie.
Yeah, thank you. I had fun.
Thanks.